Binomial theorem, the last little thing in this unit. This is Newton's baby. He developed this.
Good job,
Newton's a pretty smart guy. Binomial theorem is used to expand any binomial of the form x plus y to the n, where n is a whole number, without actually multiplying the binomials. So I just gave you the different exponents 1 all the way down to 5 just because we want to start looking at some patterns. So obviously anything to the 0 we know is 1. If the exponent is 1, who cares? Squared's okay. We can FOIL. We have a method for that. Cubic, it's a bit more work, but we can multiply it out. Well, what if I gave you x plus y to the 4? So yesterday in the homework there was a quartic, and some people were like, how do I do this? Well, you'd have to multiply 2, FOIL them out, and multiply the other 2 and FOIL them out. You have to FOIL that all out. So that's going to take a lot of work. That's really what binomial theorem is for. I'm going to show you how to do this quickly without actually having to multiply them all out. Look at x plus y to the 5. How long would it take you to FOIL out 5 binomials? Right, and you got to make sure you don't make a mistake. You don't drop a negative if there was one. You collect all the like terms. So that's what this is for, is just a quick way to be able to do quartics, quintics, etc. So all we want to do is start looking at some of the patterns in here. And there's going to be 5 of them in total, and that's going to form the basis for binomial theorem. So first thing I want you to look at are the x's in each of these. So x, an exponent is 0, no x in the answer. X exponent is 1, x in the answer. X exponent is 2, we have an x squared, and we have an x. And then technically we have something in this term, although we don't see it. We have an x to the 0. So just show that again. We have an x squared. The next term is an x, and the last term, although you don't see it, is an x to the 0. Take a look when the binomial is cubed. We have an x cubed, then an x squared, then an x, and again at the end we don't see it, but we have an x to the 0. Okay, so what should we have if the exponent is 4? X to the 4, x to the 3, x to the 2, x, and x to the 0. What should we have if the exponent is 5? Do you see a pattern there in the exponents on the x? So the exponent on the x starts at, I'm just going to call it n in general, because what we're really trying to do is develop this for x plus y to the n. So if the exponent is 5, it starts with 5. If the exponent was 10, guess what it would start with? X to the 10. And decreases by 1. To x to the 0. What about the y? Explain opposite. Okay, so let's start at the bottom this time and look. Our y at the 5 is at the back, and our second last term has a y to the, and then, we don't see it, but we know it's y to the 0. So the exponent on y starts at 0 and increases by 1 to x to y to the n. Well, why is this pattern going to become important? More because I say so. So how is that going to help us be able to quickly expand the binomials without actually using any multiplication? Yeah, it's going to tell us how many terms there are. That's really what this is for. So I want you to take a look. Exponent of 0, how many terms? 1. Exponent of 1? 2. Ooh, exponent of 2. Okay, let's go down. Exponent of 5? 6. So the number of terms The number of terms. That's not the hashtag of terms, that's the number of terms. Is one more than the exponent. So if the exponent is n, the number of terms is n plus 1. So if I ask you to find x plus y to the 9, we already know how many terms is there going to be? 10. And the x is going to start with 9 and go all the way down to 0. And the y is going to start at and go all the way up to 9. So we already have the number of terms. We already have what the exponent is on the x, and we already have what the exponent is on the y. Okay, so we already have a bunch of pieces without actually doing any multiplication yet. Going back here, I want you to look at each of the individual terms in the expansions, and I want you to add up the exponents. Okay, so let's start in the middle just for fun. What's 3 plus 2?
5.
What's 2 plus 3? What's 4 plus imaginary 1? Ooh. What's 4 plus imaginary 1?
5.
What's the sum of the exponent in that one?
5.
And here?
5.
Coincidence? Okay, check the line above. Does it have the same property? Okay, so 4, the total here is 4, 4, 4, 4. Okay, let's just double check again. Next one is
3, 3, 3, 3.
That's how we were so good at multiplying out polynomials when you guys were still struggling, because we knew binomial theorem. So we knew how many terms there should be. We knew the sum of the exponents. We knew what all the terms had. The sum of the exponents. Ooh, you can't see that. The sum of the exponents in each term equals n. So we already know the number of terms. We already know what the x starts with and ends with. We know what the y starts with and ends with. We have a little check that we can do the sum of the terms to make sure we're on. The last piece, what we don't know yet, is the coefficients. So let's just take a look. Coefficient here is imaginary 1. Here it is. What do you notice there about the numbers? The first and last are 1. The second and the second last are 5. And the two middle is 10. So 1, 5, 10, 10, 5, 1. Okay, let's look at the line above. Imaginary 1, 4, 6, 4, 1. Okay, so what's the pattern there? What do you see? Sir David, a little bit louder. First and last are always going to be 1, so we can check 1, 1, 1. Okay, what's the other pattern? Okay, so these are 5 and this is 5. 4, 4, 3, 2. Okay, what else do you see?
That the middle ones are higher.
The middle ones are the highest. Okay, check the lines above, make sure that's still true.
Well, that really goes up.
Okay, what else?
On the next to the third line, if you add the 3 and 3 together, it makes the 6. So put the next line together, 4 and 6, it makes it 10.
Ooh, so 3 and 3 equals? Ooh, 4 and 6 equals? Ooh, I like that. What else do you see? Do you notice they go up and then go back down? We call this symmetric. Okay, if I were to draw an imaginary line right through the middle, what do you see? The two halves are exactly the same. Okay, so that's the first pattern we want to note, is that the coefficients are symmetric. And then Luke was actually about 2 seconds ahead of me. And then you guys were so good, you already noticed some of the patterns we're about to talk about. So all I've done here is I've just taken away the x's and y's. So this is the exact same as before, just looking at the coefficients. And when you look at them like this, there's so many freaking cool patterns in this. So we already talked about the first is always going to be, and the last is always going to be 1. So you get this triangular effect. Take a look at the second diagonal row. 1, 2, 3, 4, 5, this way. 1, 2, 3, 4, 5. So what would the next row contain? 6, okay? These you may not recognize, but 1, 3, 6, 10, etc. are very special patterns. Anybody know what 1, 3, 6, 10 are? They're called triangular numbers. So if you were to draw, and you don't need to write this down, but if you were to do 1 dot, then 2, 3 dots, then 6 dots, what do they form? Triangles are called triangular numbers. And so you end up getting it this way and the other diagonal. There's also that symmetry pattern that we just talked about. But the trick is, what Luke was ahead is, if we take any two terms and we add them together, we get the next row. Okay, so if I took 4 plus 6, we're going to get 10. If I took 1 plus 4, we're going to get 5. This is a very, very special triangle. It's called Pascal's triangle. Yeah, Pascal was a very famous French mathematician about the 1600s. And he founded, not knowing at the time, but he founded the computer language called Pascal. That's where it comes from. And Pascal's triangle is formed by taking the previous two terms, so the ones above, and adding them. So we can get the next row because we know it starts with 1 and we know it ends with 1. And then all we do is add. What's 1 plus 5? Oh, you're ahead of me there. And we can keep going to infinite. Let's say what the next row is, but not write it down. It's going to be 1, 7, and you can keep going forever and ever and ever. And Pascal died, I don't know, 1600 and something. And since then, they have found so many different patterns in his triangle, they don't even know yet if they're done finding patterns. There's fractals in this, if you've heard of fractals before. There's Da Vinci numbers, Fibonacci numbers are all in this. And we don't know why yet. We don't know the significance. The coolest thing they determined long after his death is it's actually all formed with combinations. So the first row is a 0C0. No objects, picking none. How many ways can we pick none objects from no objects? 1. The next one is a 1C0 and a 1C1. So one object in no ways, one way. One object in one ways, one way. Then it's a 2C0, a 2C1, a 2C2. So two objects don't pick any is one way. Two objects picking one. Well, you can pick the first one or the second one, which gives us 2 ways. 2 picking 2 gives us, and it just follows all the way down. And that's ultimately why it's in this unit, because it's all formed with combinations. Pascal didn't even know it. He was so ahead of his time. And his first name was Blaise, which is just such a cool name. Blaise Pascal.
He's basically like the original hipster.
Kind of, yeah. He was kind of a rebel. Blaise Pascal. So what this is going to give us in a second is a way to find all of those coefficients without actually doing any math. To find all those coefficients without actually doing any math. So there's the theory behind what we're going to do. Let's actually do some questions now. So grab your paper. And what we really want to do is the next row on that table on the first part of the note. So we had done x plus y up to the 5. We're now going to do x plus y to the 6. I'm a color person, so I'm going to color code. If that's not your thing, don't worry about it. And what I'm going to do is do this in pieces. I'm going to first do just the x piece. Then I'm going to do the y piece. Then I'll worry about the coefficients. So before we even begin, we want to look at how many terms is this thing going to have. And we already looked at the pattern between the exponent and the number of terms. If the exponent is 6, how many terms is the answer going to be? 7. So it's always n plus 1. I know the x is going to start with 6 and go all the way down to 0. So what I'm going to do is just set that up first. So I know the first term has an x to the 6. And I'm only putting brackets here because it's going to matter later when this has a coefficient attached to it. And then I want to leave lots of space, and I'm going to put an x to the 5. And the third term has to have an x to the 4. And the fourth term has to have an x to the. And the fifth term has to have an x to the. And the second last term has to have an x to the. And the very last term, which is the 7th, has to have an x to the 0. And I'll simplify all those in a second. I'm just setting it up right now. And again, this just comes from looking at the patterns. And I'm going to switch colors now, and I'm going to do the exact same thing with the y. Y is opposite. It starts with 0 and goes up to 6. So I know I have a y to the 0, and I have a y to the 1, and a y squared, and a y cubed, and a y to the 4th, and a y to the 5, and a y to the 6th. And again, the brackets are going to become important later, so I'm just getting in the habit of always putting brackets. Now I've got a built-in check right now. The minute I've done the 2 exponents in every term in the answer, how can I check that they're correct? Add them. 6 plus 0, good to go. 5 plus 1, 4 plus 2, 3 plus 3, 2 plus 4, 1 plus 5, 0 plus 6. So I got a built-in check at this point. The coefficients are going to come right from Pascal's triangle. So I will show you here so you don't have to flip. If the exponent is 6, we need the 7th row because it matches the number of terms. 7th row has 7 terms. So we actually put it here already. So right from Pascal's triangle, we know the first coefficient is going to be 1. Then, and then, and then. I'm visual, so what I like to do is box the terms just so we remember what's going to all be multiplied together. If you're not visual, don't bother. But I like to just remind myself, okay, I have to have 7 terms at the end. And all I'm going to do is multiply those 3 pieces together. So a 1 times x to the 6, x to the 6. Well, y to the 0 is the same as what? 1, so I don't need it. So that whole term, when we simplify it, gives me x to the 6th. Second term, I have 6, x to the 5, and y. And I don't need to write the exponent of 1. We know that it's there. The third term, I have 15. Smush it together, x to the 4, y squared. The middle term will be 20x cubed, y cubed, plus plus perfect. We know x to the 0 is 1, so we have 1 times y to the 6 gives us. There's the expansion without actually multiplying. Nobody actually multiplies out quartics and quintics into the 6. Once you know binomial theorem, that's what you use because it's so much faster. Plus, there's lots of apps online that will do all this for you. So I just picked Wolfram Alpharum, which if you know him is just a fantastic site. And so x plus y to the power of 6, already built into the computer for us. There's the expansion right there. I know, but you understand what it's doing, right? So nobody actually multiplies these out. We just use computer programs because it's way easier. But now you know the theorem behind where it comes from. Okay, well, let's do one when it's not just x and y, and there's more stuff involved. There's coefficients and a whole bunch of stuff going on. So we're going to do 2x minus 3y to the exponent of 3. First thing we ask is how many terms, because that's going to help us set up all of the little things we need to multiply. So if the exponent is 3, we know there are 4 terms. Some people like to do blanks, and I like to really space them out so I have lots of room. If you want them all on one line, put them all on one line. If you don't like the blanks, don't use the blanks. We know the first term, which in this case is 2x, not just x. So 2x is going to start with the exponent of 3 and go all the way down to 0. Okay, so 2x to the 3, 2x to the 2x to the, and 2x to the 0. The negative 3y, you'll notice I'm including that negative with the 3. So negative 3y is going to start with 0 and go up to 3. So negative 3y to the 0, negative 3y to the 1, negative 3y to the 2, negative 3y to the 3. And you'll see in this one why the brackets are so important, because, for example, in this term, the negative 3 and the y are going to be squared. That's why I just get in the habit of putting everything in brackets. Now we need to do the coefficients. You have two choices. You can memorize Pascal's triangle and write it out, or you can use the combination. So we did the last one with the triangle. I'm going to do this one with combinations. If you want to use the triangle, the row matches the number of terms. So you would have to write out the triangle to the 4th row, and that would give you the coefficients. Let's practice with combinations. So each of these are going to be a combination. The n value is always going to match the exponent in the question. So this is going to be a 3c something, 3c something, 3c something, 3c something. The r value comes from its position in Pascal's triangle, which is the same as the last exponent. So these are always going to match. So this is a 3c0 because this is 0. This is a 3c, 3c, 3c. Okay, so I'm just going to make a note for the first one. This and this will always match because it's position in Pascal's triangle. Completely up to you. You can memorize the triangle. Ooh, I meant to color code the coefficient. That bothers me now. You can either memorize the triangle, write it out to the row you need, or you can just use the patterns in the combinations, whatever you want. Again, I like to box. If you're not a boxer, don't worry about it. Sometimes the blanks just help. And this time, because I have lots going on, I'm going to do each piece separately. So I'm going to start with a 3c0. Well, NC0 was one of the patterns we looked at yesterday with combinations. What's NC0? It's always going to be 1. A 2x cubed, that's an exponent law from grade 9 that just says we cube each part. So 2 cubed is 8, and x cubed becomes x cubed. And a negative 3y to the 0, well, what's anything to the 0? So you don't need to put these ones. It's completely up to you. I like to have them in this step just so I know I had those 3 pieces that I multiplied out. The second term, a 3c1, that was also one of the patterns we looked at. An nc1 is always going to be, no, because this one was 1. An nc1 is n, which in this case is 3. 2x squared, 4x squared, and a negative 3y to the 1, negative 3y. And I'll simplify all that up in the next step. I'm just doing the 3 pieces right now. Well, once you've come halfway, so we've done 2 out of the 4 terms, you've already calculated all the permutation or the combinations that you need. Because what was our last pattern? They're symmetric. So once you've come halfway, we know that they just repeat themselves. And the third pattern we looked at yesterday is we said if the 2 r's equal up to be n, they're the same. So the one we did was 7c3 is the same as 7c4. And we said, for example, 5c2 is the same as 5c3. That's because the triangle is symmetric. That's why these 2 are the same, and these 2 are the same, and these 2 are the same. Okay? It all comes just from the symmetricness. Is that a word? I don't think so. Let's pretend it is, of the triangle. So we've got 1, we've got 3. We don't even need to do much thinking here. 3c2 has to be what? So if it went 1, 3, and there's 4 terms, it's got to go back down. 3 and 1. So this one has to be 3. 2x to the 1, 2x. Negative 3y to the 2, so we have to do negative 3 squared. Ooh. 9y squared. And the last term, ncn, or 3c3, or 5c5, or 7c7 is always going to be 1. A 2x to the 1. 2x to the 0 is 1. And the last one, we just need to do negative 3 cubed and y cubed. And then I'm just going to multiply the 3 pieces. So a 1 times 8x cubed times 1. The second term, I've got 3 times 4 times 3, so 3 times 4. 12 times minus 3. And then we just smush the pieces together, x squared y. The third term, I have 3 times 2 times 9, so 3 times 2 times 9. And then smush the variables together, xy squared. And the last term, don't care about the 1s, negative 27 y cubed. That's as hard as it's going to get. Questions so far? That's where we're going to pause today because we're going to do the rest of it tomorrow because I don't want you to mix up how to find a specific term versus the expansion. So we're going to do one more example together that you're going to make up. What exponent would you like to do? 5. Sounds great. Give me the first term in the expansion. X. Way to branch out and challenge yourself. Okay, let's put a negative because they're a little bit harder. 4, and let's throw a b in there. Hey, why not? So it's not always going to be x and y. Let's do a b. First thing you want to ask yourself is, how many terms? Because it's going to help you set up the answer. How many terms does this have to have? 6. Okay. So again, some people like blanks, some people don't care about the blanks. Now this is how I set it up quickly. I say I know I'm going to have a combination. I'll fill in the n and r after. I know I'm going to have x to the something, and I know I'm going to have minus 4b to the something. So I set those all up before I actually do the exponents. Then I start with the x, and all you need to remember is does it go up or down? It goes down, so it's got to start with a 5, 4, 3, 2, 1, 0. Okay, then I do the second term, which is in this case is the negative 4b, and it has to start with 0 and go up. So 0, 1, 2, 3, 4, 5. I do the check right here, and I say, okay, let's just check the exponents, and what are we checking for? We add them. So 5 plus 0, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, 0 plus 5. So just double check, it adds. Then I do the combination. The n, so the first number is always the same as the exponent. So 5, 5, 5, 5, 5. And the r is always the same as the second exponent. And if you'd rather draw out Pascal's triangle, that's fine. You can do that as well. You need the 6th row of Pascal's triangle. But I just match this, has to be 0, 1, 2, 3, 4, 5. Then I box because I'm a boxer. That's funny. First and last terms are always the easiest because we know a 5c0 is 1 and we know anything to the 0 is 1. So all I'm left with is x to the 5. Then I'm just doing the 3 pieces term by term. A 5c1, well, nc1 is always equal to n. So I know right away that this has to be 5. X to the 4. And what's anything to the 1? Itself, and I'm just going to be really careful to keep those brackets around the negative 4b. Why do I need the brackets there? Because it's multiplication, and if I were to drop those brackets, what I've said is 5x to the 4 minus 4b, which is a binomial. Okay, so just keep the brackets around everything when it's negative. Okay, 5c2, you can either do it with your calculator, you can memorize it, or you can think about Pascal's triangle, 1, 5, something. 10, x to the 3. And then just make sure you're squaring that negative 4 and the b. So negative 4b squared would become 16b squared. We're halfway out of our 6 terms, so we've done the first 3. So what do I know about the coefficients? They're going to repeat. So it went 1, 5, 10. Now they're going to become 10, 5, 1. So I know the next coefficient is 10. Because Pascal's triangle goes up and then goes back down. So 1, 5, 10, 10, 5, 1. Right? They're symmetric. Or you could do that in your calculator, or you could write out Pascal's triangle. X squared becomes x squared. Negative 4b cubed, so negative 4 times negative 4 times negative 4. Sorry? Negative 64b cubed. Again, coefficients went 1, 5, 10, 10, 5. X to the 1, which will be x. And negative 4 times negative 4 times negative 4 times negative 4, which you would be able to use your calc, or you can just do 64 times 4 and then steal my thunder. And the last term, I know an NCN is 1, and I know x to the 0 is 1, so the only thing I have left is the negative 4b to the 5. 1024? B to the 5. we doing so far? Okay, so that's a term, that's a term, that's a term, 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 term. I like to double check. Do I have 6 things circled? Why do I need 6 things circled? Because I need 6 terms from the beginning. So first term, no big deal, x to the 5. Second term, smush it together.
Negative x plus 116x to the 3t minus 640x squared plus 1,280x e to the 4 minus 1,040 to the 5.
There's the expansion. But how long would it take you to do x minus 4b times x minus 4b times x minus 4b 5 times? How long is that going to take to FOIL out and not make a mistake and not miss a term and do everything correctly? That's why we have binomial theorem. Grab your phones. I'm going to give you a QR code to scan. Nope. I may give you a QR code to scan. This is just the generator that I just showed you earlier. So to check your answers, you can just generate. So we'll check this one once we get this up.